Standard error of estimate, or SEE. Standard error of estimate represents the dispersion of the errors around the regression line. So the blue line here is our regression line itself, but you can see that the regression line simply cuts through the observations. Therefore, there's bound to be errors. In other words, if you look at this observation here, you could see that for that value for x, the regression estimated or forecasted y to be right there, but the actual value for y was right there. So that difference right there is the error, and hence the term standard error of estimate. In other words, what is the typical error that results by using this regression, i.e. this blue line, in order to forecast the actual observations. Now, standard error is a lot like standard deviation, and that's why what I'm going to do is I'm going to use standard deviation or its variance as the template in order to construct the framework for standard error of estimate. So the first thing we're going to note is that whenever you're quantifying dispersion, we always square, and you could see that right here. Ladies and gentlemen, this error is positive, that error is negative. If you add up all these errors, they're going to cancel each other out. So it'll give you the impression that there's zero errors. That's not true. So if you want to know how big the errors are, what we got to do is we got to convert the negative errors into positive errors as well. How do we do that? Square. So first I want you to know why we're squaring these standard errors or standard deviations. Because again, we're only interested in the size of the errors, not the direction. All right. So let's see what we remember about variance. Now, variance is the dispersion around the mean. And the way we quantify it is as follows. We look at the individual observations and how much it deviated from the mean. And then again, we square so that the positive and negative dispersions don't cancel out. And then we divide it by the degrees of freedom, which in this case is n-1. And by the way, the numerator here, this whole numerator, you can see where the name comes from. It's the sum of squares for the total variation in y. So whenever we talk about the total sum of squares, we're talking about total variation. What is total variation? What was the total deviation of the actual observation from its mean? So that would be the technical definition of total deviation. So ladies and gentlemen, now that we have our framework for standard deviation, we can use the exact same template in order to construct the framework for standard error of estimate. So first of all, what is the big difference conceptually between standard deviation and standard error of estimate? While standard deviation or variance looks at the dispersion around the mean, standard error looks at the variance around the regression line. That's the big difference. That's the big difference. So if you look at standard error, it's measuring how dispersed these individual observations are around the regression line. Now the regression estimate is y hat. So whenever you see that hat, it means that's our estimate for what the value for y is. So then look at the similarities. So we still got to do the sum because we want to measure the dispersion on all the observations. So you still have that observation, but whereas variance looks at the deviation from the mean, standard error looks at the deviation from the regression line. That's the big difference. That's the main difference. And then of course we square, we know why. And the other difference is the denominator. So when you're calculating standard error, we have to take into consideration the number of independent variables that are in the regression itself. So that's what K represents over there. So if there's only, in our example, there's only one x, one independent variable, because it's a simple linear regression. So there's only one independent variable. So K would be 1. But if we're looking at a multiple linear regression where there's multiple variables, then you just plug in the number of independent variables in for K. So that's it, ladies and gentlemen. So rather than saying n-1 in the denominator as we did for variance, for standard error, it's n-k plus 1. And that's it. That's the only difference. And then after we compute SCE squared, and this is the same process as variance. Like you first do the square so that the positive and dispersions don't cancel each other out. But then once you have a number for variance, you then remove the square by taking its square root, and it's the same thing here. So after we've calculated SCE squared, you remove the square by finding its square root. And so what are the points we want to know about SCE? Now remember, keep it high level. What this E stands for, error. So let me ask you this. Do you want your model to have high errors or low errors? So keep it high level. Of course, we want low errors. So therefore, if you say the greater the SCE, right there, I know that this is bad news because you're saying greater errors. So let's see what the consequences are. That would indicate that we have more dispersed observations around the regression. So let me just show you with our visual framework here. So if SCE is greater, what will happen is the following. Let's just pick this observation. So rather than the observation being here and the error only being this much, a greater SCE would imply that the error is even greater, which means our model is even more way off than before. And there it is. It would mean greater error, and therefore the final conclusion is that this model is less reliable, i.e. it's less significant.